It is often the case that point estimates are not sufficient for real-world applications. For example, when estimates of uncertainty are necessary for our prediction or to ensure generalization when training on small datasets. Medical imaging, autonomous vehicles, and financial operations all fall under these categories. In these settings, it is necessary to view the problem with a Bayesian lens and estimate the posterior distribution of the model parameters. With large models, it is hard to estimate the posterior joint distribution using a direct application of Bayes' rule or straightforward Gibbs sampling. Variational inference allows us to choose an approximate posterior distribution close to the theoretical one by minimizing a corresponding Kullback-Leibler divergence. For some forms of approximate and posterior distributions, like Gaussians, this KL term can be derived in closed form. But recent results have shown large neural networks, even with the Gaussian distribution, complicate training and lead to poor accuracy, even for simple datasets. Unfortunately, for other choices of approximate distributions, there does not always exist a closed form expression for the KL, and so further estimation is required. Monte Carlo sampling is often used to estimate the KL term. It is a simple and unbiased estimator, which is asymptotically exact. However, good estimation requires a large number of MC samples, especially when the model is large. For standard neural network sizes, the number of MC samples required to accurately estimate this KL can grow to several hundreds or thousands quickly. Current methods of Bayesifying deep networks fall short for this reason. Their size limits the number of MC samples possible during a single forward pass, leading to worse KL approximation, eventually resulting in both longer training times and lower final accuracy. This intractability stems from standard implementations of MC sampling in existing deep learning packages. Specifically, the computation graph constructed naively depends linearly on the number of samples needed for high-quality KL estimation. Increasing the number of samples results in a GPU memory explosion. Is there any way to preserve the size of the graph independent of the number of samples? In other words, can we increase the number of MC samples up to 1000 without exploding GPU memory? One possible solution is gradient accumulation. This standard method is used to collect gradients from several forward passes. Memory consumption is equivalent to one forward pass, but time complexity is proportional to the number of forward passes, still far from ideal. First, to talk about the size of the computation graph generated by Monte Carlo approximation, it is important to define what size means. To define the size of a computation graph corresponding to an MC approximation, we introduce parameterization tuples. Consider a function f where wi can be sampled as a function of a parameter theta and an ancillary random variable c. If there exists functions g, n, and t such that f can be expressed as g of n and t, then we say that it is a parameterization tuple p for the function f. Let dp be the dimension of n dot t, corresponding to the number of nodes requiring gradients with respect to theta. Now consider the size of the previous graphs according to our parameterization tuple. With one MC iteration, the size of the graph is 3. That is, 3 nodes interact with the parameters. With 2 MC iterations, it is 6, and with 3 MC iterations, it is 9. However, notice that the same graph with 3 MC iterations and size 9 can be reparameterized in such a way that dp is 3, equivalent to a graph with 1 iteration. Can we identify distributions such that the size of the graph generated by an MC approximation is independent of the number of samples? Let's take a look at the Pitman-Koopman-Dormois theorem. It states that, for exponential families, there exist sufficient statistics such that the number of scalar components does not increase as the sample size n increases. While the theorem results cannot be directly applied in our case, it still suggests considering members of exponential families as candidates for our distributions, which lead to computation graphs with size independent of the number of MC samples. In our paper, we provide theorems which describe how to identify such distributions in general. Here, we provide a summary of distributions common in Bayesian settings under which a reparameterization allows us to increase the possible number of iterations without a linear growth in space. Loss minimization in Bayesian neural networks requires dealing with two terms, the KL term and the likelihood term. In our paper, we discuss how to apply reparameterizations to both of these terms. Our method significantly outperforms gradient accumulation in runtime. Moreover, the larger the number of MC iterations we run, the bigger the gap for batch time becomes. For common deep networks in vision, our method reduces the model size on the GPU and allows us to increase the number of MC iterations to over 1,000 at almost no cost in GPU memory. This allows us to use this memory for increased batch sizes rather than for MC samples. Application of our method also results in a significant reduction in training time per batch. Bayesifying these networks enables the ability to measure confidence in predictions. For a standard computer vision dataset, we achieve competitive accuracy on subsets of the data for which our model is highly confident, despite a fully Bayesian model representation. Additionally, on a brain image classification task where both the models and inputs are high-dimensional, the benefit of additional MC samples becomes clear. The variance over multiple runs is smaller, allowing practitioners to be more confident in the final predicted posterior. Our proposed MC reparameterization is easily accessible via an API in PyTorch. Several different versions of popular networks are implemented, such as ResNets and DenseNets. Only a minimal change in an existing programming interface is required to incorporate our method. Here, we show an example of how to implement your own version of the Bayesian neural network using our API. Simply import our Bayesian layers module, which provides functional wrappers for existing basic layers, and redefine the forward function appropriately. We identify computation graphs for MC approximations that grow linearly with the number of iterations, which is undesirable. We introduce parameterization tuples to measure the size of these graphs and identify sets of distributions for which it is possible for graphs to be constructed independent of the number of MC iterations. We find that it is now feasible to run a large number of MC iterations for large Bayesian neural networks and provide an easy-to-use API for developers and researchers.